Yeah, Anandan sir, you can start now.
Okay, thank you. Ma'am.
Yeah, okay.
Good afternoon, Wonderland. I think this is the wonderful afternoon. I am very much grateful to the management of Caltech University. First, giving thanks to the management, giving me an opportunity as came to welcome address for this webinar. Um, Titled Energy Efficiency in Wireless Networks by Dr. Albert Lysko. And this is hosted by the Termstruck Solution by Master of Series Event. Uh, Thank you for the Termstruck solution also. And all the students are very eager and doing a beta degree with various substreams also. This gives an insight about their minor project or major project also. We can start the session by I welcome you, Dr. Albert Willisor, to giving the lecture, and also welcome the Team Step Solutions organizer also. Thank you. The session is going to Dr. Albert.
So thank you, sir. Thank you so much for the introduction. So before we start Dr. Albert's session, I would like to give some short introduction about him. Dr. Albert is an award-winning engineer, researcher, and innovator specializing in wireless communications and networking. And he holds a PhD from the Norwegian University of Science and Technology and currently serves as the principal researcher at the Council for Scientific and Industrial Research in South Africa. And additionally, he is an adjunct professor at the University of Cape Town and an extraordinary researcher at Northwest University, South Africa. And Dr. Albert career spans both industry and academia across Europe and Africa, with his extensive experience and expertise spanning multinational corporations and regulatory bodies. And his extensive experience and expertise have made a significant impact in the field of wireless communication. And Dr. Albert's pioneering work at the CSIR in TV white space technology has been particularly is noteworthy. And his experimental research is facilitated the internet access for over 20,000 users across the two African countries and contributed to the establishment of national TVWS regulations in South Africa. And his efforts is also influenced the DVWS regulations in Ghana and the United States. And currently, Dr. Albert's research interest is a focus on 5G and 6G technologies and energy efficiency in wireless networks. And his work is driven by a commitment to improving the connectivity and technological innovation, which has tangible the benefits for both urban and rural communities. And throughout his career, Dr. Albert has achieved the numerous accolades, including four Best Paper Awards and various national and CSIR awards also. And he has authored the three patents, a book, two book chapters, and over 100 research papers and articles. And his his contributions extend beyond the research, as evidenced by his roles as a general chair and technical chair in several international IEEE conferences and fellow of the South African Institute of Electrical Engineers and a senior member of the IEEE. Dr. Albert is also recognized for his leadership and volunteer efforts within the IEEE, underscoring his dedication to advancing the field of wireless communications globally. At the end, I would like to introduce to the motto of Dr. Albert. It's the main motto is advancing connectivity and empowering the communities. So I would like to hand over this session to Dr. Albert, and also thanks a lot for joining us today, and over to you, sir.
Thank you very much. It is a pleasure and honor to be talking to all of you today, and thank you very much for inviting me to talk on energy efficiency in wireless networks. I would like to acknowledge that I was kindly invited by Ms. Suganti Pusiran, I hope I pronounced your name correctly, who is a co-founder and chief people officer for Thames Tech Solution. Thank you very much for inviting me to give this talk. I would also like to highlight that the Indian government's National Digital Communication Policy, NDCP 2018, aims to create a robust and secure digital communications infrastructure with a focus on energy efficient technologies and sustainable growth. The policy emphasizes the need to adopt energy efficient and green technologies in telecommunication sector and develop India-specific 5G technologies. Thus, I assume that the topic of energy efficiency is of keen interest in India. I think a good introduction was made about me, so I can skip this. Oh, 1 second. This slide, and maybe just highlight. So I'm located here in South Africa, specifically in Pretoria, and thanks to the telecommunications, I'm able to give this talk to you well, many thousands kilometers away, and at no costs to you or me. So telecommunications is a great enabler in that regard. Before going into the technicalities, I would like to share a bit about South Africa, the country where I live. So South Africa is a prime destination for tourists. It's been said that South Africa has the wildest range of flora in the world. South Africa, to some of you, South Africa may be known for hosting FIFA World Cup in 2010. South Africa has an area of 1.2 million square kilometers and GDP of nearly $1 trillion US. And primarily we export gold, diamonds, platinum, and coal, besides having this beautiful nature, as you can see in the pictures. Those facts are perhaps better known. There are a few facts that are usually less known. So out of 60 million people, which is the population of South Africa, South Africa had in the past 6 nuclear warheads and developed its own ballistic missiles, all developed inside South Africa back in the 90s. And yet, South Africa self-dismantled the programs. And I think this makes South Africa the first and probably the only country in the world that has done something like that, developed nuclear weapons and got rid of them. South Africa is also well known for its social transformations without bloody revolutions. And South Africa is often considered as a birth of the movement by Gandhi and Mandela. South Africa is also the birthplace of Elon Musk and Mark Shuttleworth. Yeah. So I work at the Council for Scientific and Industrial Research, CSIR. It's an organization similar to CSIR. Yes, in India, I believe you also have CSIR. So South African CSIR was established back in, I think, 1945. So it is close to 80 years old by now. And the mandate of the CSIR was established in 1945, and mandate of CSIR has been to do research and innovation towards improving the quality of life of people. So this is the shape of South Africa, and here is Pretoria, where I am. But CSIR also has campuses in Johannesburg, Durban, Port Elizabeth, Stellenbosch, and Cape Town. We have over 2,000 people as staff, and I think about 15% are with PhDs. Now, another highlight I would like to make about CSIR is its experience in looking at making impact for rural areas, because I think it's, again, rural areas is another commonality between India and South Africa. Both countries have a significant proportion of rural areas, and people there need solutions, energy and cost-efficient solutions. So CSIR developed Wi-Fi mesh-based technology, which was able to provide connectivity to over 200 rural schools with over 100,000 learners. That was done by about 2012. Then we moved into the research and development in television white spaces. So television white spaces is when you borrow unused channels from the TV broadcasting, and you use these channels to offer connectivity. So we started with organizing the first software-defined radio research forum and in Africa, and then running large trials with Google and Microsoft in 2013 and 2014, where we connected over 20,000 people. And later on, we developed our own television by space database. GLSD stands for Geolocation Spectrum Database. It's an intelligence data solution which controls which TV channels can be assigned in which area without causing interference to the reception of TV. We also assisted our national regulator to adopt television white spaces in the country. We assisted with development of regulations. So nowadays, television white spaces is used as a service, commercial service, South Africa-wide. But as progress, technology moves on, and so we go with it. And now we are working on the 5th generation and beyond, 5th generation cellular technologies. So we have by now we have more than 3 test beds, including open air interface, SRS run, Fraunhofer, and so on. They are based on open technologies, open code. We also implemented multi-operator core network solution and working on energy efficiency. Here is a sample of what our test bed looks like. So here we have internet and the core networks for OAI, Kumikor, Fraunhofer, and several others, connecting the mobile network to the internet. Here are the servers which play a role of base stations, mobile base stations, and the radio heads, and we are able to communicate to the cell phones. And there we look at the topics of test bed itself, because we want to be able to provide services to local industry to help it participate in a very wide and large market of mobile networking solutions. And we, as a part of it, also look at power and energy efficiency, and it's not very actively looking at network slicing research. Okay, I'll skip the details. We have developed some software and hardware tools to do the measurements, and are actively pursuing the direction of research. But let's maybe start from the beginning. All of if you think of it, the problem of connectivity is only partially technical. It is significantly an economic problem. Why? Because if you want to deploy a connectivity solution and provide connectivity to the people, somebody needs to manufacture the equipment, somebody needs to deploy the equipment, and somebody needs to run and maintain the equipment. Right. So if you can save those costs, then you can make it more inclusive. So let's start with the drive. So what is the impact? Why everybody is so keen on connectivity? What impact does it bring? So for example, World Bank estimated that mobile broadband provides 2.5 to 4 additional jobs for each broadband job. So if your mobile network operator employs 100,000 people, that means the services provided by this mobile network will create employment for 250 to 400,000 people. There are various estimates which show that offering broadband connectivity increases the GDP, which is gross domestic product. In other words, increases the economic activity in the country. And different estimates go typically between 0.5 to 2.8% increase in GDP with an increase in broadband connectivity. We also did research on this and estimated that if you provide connectivity in schools, that has a very significant economic impact in the long term. It has exponential impact. Why? Because you deploy your network solution in the school. Once it stays there, it works, it's relatively cheap to run, but each school would educate, say, about 1,000 learners per year. Which means if these 1,000 learners learn how to use internet, how to search for jobs, how to search for information, they can get better jobs with higher salaries. And that means they can pay higher taxes, which gives direct contribution to economy. Right. And that continues year to year. So you invest one time to install the equipment and pay a little bit per year for internet, and each year you reap the benefits. And once a person's salary is higher, it continues typically throughout the lifetime. So in this regard, economic impact from internet access is similar to building a highway or a road. So you are able to exchange goods and services much, much faster. And you are able to access a much wider global range of goods and services, producers and consumers. You can do automation of processes. You can share resources and information. So opportunities become pretty much endless. Let's look in a little bit more detail at the value and economics of how this works. So a mobile network operator, or just any network operator for any network, needs to make an expense. They need to invest into building infrastructure, which is capital expense, and then operate. They need to operate and maintain the infrastructure and provide services, which means there are some operational costs. right? So when you operate network, you need to pay for the data access costs. You need to pay for power, and this is the main topic of this talk, as well as you need to rent the land on which the base station is standing, and you need to do repairs. So all of it means costs. Once off for setting up and then running every month. What does it mean for the end user? When do you pay for network services? Only when you can benefit from it, right? So one, there should be a service available. If there is no service, what are you going to pay for, right? So service base stations needs to be installed and operating. That right, the end user needs to buy equipment, cell phone, for example, right? But it's some money needs to be spent. And then every month you need to pay some money for the services which are provided to you. So why would you pay all of this money? Is because it should be useful to you, right? There should be services which are relevant to you, whether it is Netflix or Google or job search or something else. So now this end user pays to the network operator. And then for network operators, in order for them to be sustainable, they need to generate some profit, which means the income, revenue, minus costs. Right. So which means there are money spent versus money invested and value produced for the users. How can we reduce? Yes, if you look at this equation, it doesn't look like you can change it much, right? Because we have had these prices for the last 10, 20 years, for example. But you can change the situation by improving certain elements of technology and regulation. So, for example, if you share infrastructure, share the base stations and share the spectrum, that means that the cost of deployment will be significantly less. And that means that it becomes more affordable to deploy more base stations, which means you can service more users, right? And especially when it comes to going into rural areas and providing services in rural areas. But let's go into a little bit more detail. So let's look at the total cost of ownership. And total cost of ownership is usually defined as how much money you need to spend to deploy the equipment and to run it, typically for 5-10 years until the equipment starts to fail. Right, here is the breakdown. I took a picture from Ericsson, that's right. And if you look at it carefully, you will see that the major components civil works, right? Network rollout, NRO, network design and optimization, NDO, and the actual radio technology is only about according to this estimate, it's about 8%, which is a good and bad part of it. It is bad because that means that major part of the costs have nothing to do with providing communication. So building metallic structure and renting the land for that metallic structure for the base station, it's just a mechanical thingy, right, on which you mount your equipment. Right, and that cost is high, and that's why this cost needs to be shared. Right, and this cost, which is only 10%, it is a cost of equipment which makes money, which provides services. And what's good about it is that you are able to upgrade the equipment often enough. Imagine if this cost were 50%, right? It would be then likely that you would be able to upgrade equipment much less frequently, which means you can improve quality of service only very slowly. So it is very useful to share physical infrastructure to reduce the costs. But let's also think that the energy is a part of that cost, right? So by sharing physical infrastructure, you also share the costs of the energy, which means you're saving and reducing energy consumption. Here is an example of research we did to estimate the benefits of the sharing. So we looked at the CapEx and OpEx, capital expenditure and operational expenses, and investment recovery period for different sharing approaches, whether we share just radio access network, RAN, backhaul, core, or combination of elements of share everything. Right, and we assumed a simple model of a small rural village, which requires only 2 base stations and which needs to be run by a rural enterprise. So according to our calculations, if these 2 base stations are run by, say, one enterprise, this would require, with a limited amount of money which they have to invest into it, that would require about half a year to start generating profits. Right. In other words, these people will have no salary for half a year, which you can imagine not easy. On the other hand, if you do full sharing of everything, it's significant. This figure drops to just 1.3 months before this they can start to generate profits. So if you share between several enterprises, it's much faster way to generate start generate profits. It becomes much more affordable. So, and part of the cost again is the energy costs, and it significantly improves return on investment time. Another factor which I wanted to mention is the cost for deployment in rural areas versus deployment in urban areas. As you can see from the statistics provided by World Economic Forum, deploying in rural areas, which are so important for both Africa, for example, in Nigeria and India, for both African countries and so for India, it is costs 3 times more to deploy wireless networks in rural areas compared to urban areas. Why? Because in urban areas, everything is close. All the suppliers are right there. Infrastructure is there, so you're just making a short extension of the power, short extension of the fiber line. Everything starts to work quickly. If you're doing something in rural areas, you need to travel long distance toward the site where you need to do deployment, to bring materials there to build the infrastructure to that site. Then you need to run fiber to that site. So it makes it pretty expensive. And as you can see, this ratio holds pretty much for the power as well. Why? Because you need to provide it to run it over a long distance. That's a pink power for the power. Okay. So I thought it is worthwhile to mention something regarding the costs. So how can one reduce costs? So one of the immediate approaches is to use lower frequencies. Right? Why? Because lower frequencies have lower propagation loss, which means you over the same you can send signal over a large distance and have the same speed. There are some technical limitations like bandwidth, etc. But let's just look at the overall overview. So this was a study done by BCG. They looked at different solutions like fiber, satellite, mobile networks in different frequency bands, television wide spaces, and the technology mix. And they looked at the target of connecting all rural Americans. So if you try to do, if one tries to do provide connectivity to all rural Americans using fiber, and fiber, I tell you, is the best solution you can get, because you have the best speed, lowest energy consumption, and so on. You need to invest the most amount of money, so between 45 to 65 billion US dollars to connect rural Americans. If you use satellite, well, satellite in theory covers large area, right? There is one or several satellites and then can cover a large area. So in theory, it's a universal solution to connectivity problem. Unfortunately, there is a challenge. It costs a lot of money to build them and to launch them. Right, I think launching is probably the lion's portion of the cost. So to cover rural America, it will cost about 30 to 45 billion US dollars. If you try to do connectivity, well, by building base stations everywhere, mobile network base stations, in usual frequency bands, it costs a lot of money, similar to satellites, right? But if you go to 700 megahertz band, your cost goes significantly down, lower. Why? Because now your base station can cover more area, right? And if you subtract spectrum costs, the costs go down even more and become similar to using television wide spaces. Here, I should mention, I think that study didn't take into account the energy consumption component. So the cost for TV spaces would have been a little bit lower, right? But of course, ideal solution is if you have urban area, you provide mobile networks. If you have rural areas, you use satellites. So you mix and match as appropriate. And as you can see, you can drop the cost by a factor of what, about 5, 6 for connecting the entire country. So let's now dive specifically into energy efficiency component. And I should mention that telecom operators already now account for 2 to 3% of the total global energy consumption. I would also like to make another remark that according to the Moore's law, if you apply Moore's law, as the silicon shrinks, remember from your 30 nanometers to 20 to 10 to 6 to 4 and so on. That means CPU or processing power consumption goes down. But signal to noise ratio and the link connectivity must remain, right? So it introduces a fundamental constraint. So you can reduce the amount of power which is consumed by the core network and by much of electronics in the radio access network. But you would still need to send out the same amount of RF power, radio frequency power. I will come back to it just now. Here, I would like to just make a quick mention. So I spoke about the Indian government's national digital communication policy, which was an excellent initiative. So it's also worth mentioning that Indian railways have plans to use 5G for energy efficiency, to optimize energy management systems, monitor systems in real time to reduce energy wastage. Right, and these developments, they demonstrate growing importance of energy efficiency in India's 5G landscape. With India's players, research institutions, and government entities are already working on innovative solutions to address the country's unique challenges and requirements. Right, so here you can see a number of different initiatives coming from different sides of the ecosystem, which basically tells the energy efficiency is very important for India. It's a huge country with huge population, and reducing energy consumption can make a big impact. So let me start with the extreme example. Right, what we would like to have is things which do not consume energy at all, which do not require battery or mains power. And here you have example of RECT antennas for Internet of Things IoT applications. So basically, these type of systems, they get the energy from whatever is being already emitted in the air. You have television broadcasting, you have mobile base stations, you have Wi-Fi, and so on. They all emit some amount of RF energy, and this energy can be used by these devices, right? Of course, if you think that they can only store on the order of 10 millijoules of energy, and that takes on the order of 10 minutes. And that's from a source with just 4 meters away. So the ability, the technical capability of this type of devices is still very limited, because the amount of power available in this way is for now very limited. But in the future, hopefully, as silicon shrinks and consumes less and less, it becomes more and more viable. Now, the next question one would ask, right? Do we need to worry about power consumption if there are, say, so-called renewable energy sources like solar are available? And if you talk solar, normally you have to have a battery next to solar. So you always have to consider both of them. And if you can see, there is a great progress that's been made. In 2010, your cost was this much. You see the red bar. And by now, we have our cost what's on the order of close to 10 times less, right, to produce energy from the sun. So solar panels became close to 10 times cheaper than it was just 15 years ago. The price for the batteries, it's here is example of lithium-ion batteries, also dropped drastically, as you can see, from $7,000 in 1991 to $181 in 2018. So huge improvements have been made. Yet, as you've seen from the previous slides on Ericsson statistics, we are still far from having the problem solved. So the motivations for energy efficiency are multiple. So to reduce operational costs, and remember that I'll talk about it later. There is an constant increase in traffic. So more traffic means you need to process more bits, which means you need more energy. So you want to reduce the energy consumption by improving energy efficiency. You can also think of it from the point of view of general sustainability and making the world more green. Because if you consume energy, it has to be generated somewhere, right? So something should have happened. Some effort and resources and power should have been spent to set things up to generate the energy. So if you don't need to build a very big power station, you can just maybe build a small power station, and it's enough, it's good. In South Africa, load shedding is a problem which we are trying to solve, because our capacity of power generation is insufficient. Here is a blunt example I wanted to give, right, of inefficiency in mobile networks. So, and this example is from Ericsson. Right. So, a reasonably modern 4-port MIMO dual band radio can deliver what, about 160 watts of RF power which is used to transmit information. Right, that's for a base station. But in order to do that, they require over a kilowatt of electric power. So your efficiency is here, what, about 16%, which is horrible. So let's dive now into what is energy efficiency. Let's start with energy. So energy is an integral of power over time. If I try to simplify this equation, if your power consumption is constant, that basically means energy equals power times time. Right. So if you want to reduce energy consumption, you need to reduce power, or you need to reduce the amount of time during which you consume this power. Right. That immediately gives you an idea of how can we do such a thing. So you either need to reduce the amount of time when you consume power, and for example, you put base station to sleep. So if no users are connected to base station, you put base station to sleep. Or only few users are connected to base station, then you put half of the components on base station to sleep, because you don't need that much of processing capacity, or don't need that much of power. Right. Until such time when it's needed again and you wake them up. The other option is to reduce energy consumption is to reduce the power, right? How do you reduce power? For example, if you use omnidirectional antenna means it radiates all around you antenna. The same thing, all around antenna. It's very convenient. I mean, most of Wi-Fi until recent used omnidirectional antennas. Why? Because it makes the technology very simple to design. And the only sacrifice is really energy consumption. Right, but what's being done in modern Wi-Fi as well as in mobile networking and other type of communications, they, instead of spreading energy everywhere, right, they try to use directional antennas and MIMO and do beamforming, which means you only communicate within the range of angle where your users are. And you don't transmit here, you don't transmit there, you only transmit within this angle towards your users, which significantly improves the energy consumption. So I'll skip this lovely summary for now. I think say the deep details of why you, as I mentioned, you need over 1 kilowatt of power in order to produce just around 60 to 160 watts of RF power. Right? Why? Because here you want to transmit your 60 watts, but you lose half of the power as it goes up through the cable, which means you need to transmit here, I mean, to produce 120 watts. But your power amplifier would have efficiency of 12% if you want high linearity, which means you need to deliver about 1 kilowatt to this power amplifier and cool it down. If you need to cool it down, which means you need air conditioning, right? Then there is all the signal processing, which you also need to cool down, and so on and so forth. So if you add it up, you can easily come up with well over a kilowatt of power to produce useful amount of 60 watts, which is pretty horrific. As I mentioned as earlier, and here are the plots to highlight it, here is the traffic demand, right, for the past and for the future. So it's the traffic demand going up exponentially, continuously, non-stop. which means even if even though, for example, 5G networks are theoretically more efficient than 4G networks, remember they're efficient per bit. So let's say you made them 10 times more efficient per bit. But if your improvement is fixed 10 times, but your traffic goes up exponentially, obviously energy consumption will increase overall. Right, and now all the numbers put it together with business models for mobile operator. So there are more applications, more speed required, more devices there, which means there is more traffic, which means there is more energy consumed per site. Yet the price per gigabyte, the amount of money which you are willing to pay mobile network operator, only goes down, right? You don't want it to go up. So it becomes more difficult to make business sustainable. So there is a really strong need to make improvements in energy efficiency. There are various technical reasons and for energy efficiency. For example, if you want higher data rates, you need more bandwidth. And wider bandwidth typically increases your power consumption and energy consumption. Now, if you want to have devices which are faster, have lower latency, so that they respond instantly, right? Which means you cannot afford to put them to sleep, right? Because you want instant response. So another challenge. If you want to use massive MIMO, right? In massive MIMO, there is certain power which would be consumed by hardware components to control massive MIMO. So you have a gain from having your antenna beam narrower, but you lose a certain amount of energy on being able to do this control. So there is a balance, unfortunately. And so on and so forth. I won't go into all details. Let me just roughly give few highlights. So power amplifiers, I mentioned the efficiency is quite bad, like on the order of 10% to achieve high linearity, which is required for being able to do MIMO. Right. So a new class of amplifiers, which basically do switching on, off, and use filtering to produce appropriate shape of the signal. Right, efficiency of over 90% have been reported. So there is a progress there. Now, the next item is, do you need to have many bits in your analog to digital, to analog converters for MIMO especially? So you can reduce some amount of energy somewhat by reducing number of bits which you use. And it was found that 4 to 8 bits maximize energy efficiency. At very drastic improvements you can make if you do system-on-chip design. In other words, you realize entire component on a chip. So, for example, Ericsson reported 7 times improvement in energy efficiency over the 5 years. Right, but what's the problem? That's a brilliant way to improve energy efficiencies, but unfortunately, it's very costly. Designing chips is very, very costly. Right, so if you want to design something that's going to work for 20 years, it's a good way to go. If you want to design something that you need to replace in 3 years because your standards and technologies change, it becomes expensive. Now, I remember I mentioned you can easily lose half of your power in the cable going up the base station towards the antenna. So if you put your amplifiers up on top of base station, you can remove those losses. So you can improve efficiency by 12 to 40%. Centralized radio access network architecture. So currently, most base stations, each base station, as you build it, would have its own radio access network boxes inside it, right? But it's often not necessary to have it in each station. Often it is good enough to have one box which would serve several base stations, and you connect them with fiber, right? So if you use this approach, you centralize radio access network. You can save up to 40–50% of power. Right, let me skip the cooling part. If you use MIMO, the estimates have been shown that it's possible to do, it can give improvements up to 14,000 times in terms of energy efficiency, at least for dense urban areas. Unfortunately, for rural areas, the improvements are not that significant. So for dense areas, energy efficiency was 6.7 megabit per joule. And for rural areas, only 0.15, right, which is 40 times less. Why? Because your population density in rural area is less. If you remember, how do you achieve energy efficiency with MIMO? You're able to form a very narrow beam and pencil-like beam pointing towards the user. So energy is not spent here or there, it's just sent towards user. And remember, in urban areas, you probably have 5–10 users here, or maybe it's 20 or 30. In rural area, density of people is much less, which means you have to have much wider beam, typically. Or if you build a very narrow beam. Remember, building a narrow beam means you have to use a lot of antennas and electronics. It costs a lot of money. So it's economically becomes expensive. So yes, you save on operational costs, but your capex, capital expenses, become high. Another item which I thought worth mentioning is that, unfortunately, energy efficiency and spectral efficiency are not the same. So spectral efficiency, if you increase number of antennas, you can continuously increase spectral efficiency. Why? Because you can more antennas means you can make more and more narrow beam, antenna beam. More narrow beams, which means you need to spend less energy within this beam. But as I mentioned, because you need to spend some energy on the control itself, that's why your energy efficiency curve has a maximum, optimum, right? And for the given configuration, it was around 90 antennas. But as you increase number of antennas, your energy efficiency goes down. Right. So you can choose either energy efficiency or spectral efficiency, unfortunately. Okay, for the sake of time, I will skip on the explanations, how it works exactly. I will just do a few highlights. I mentioned that, so all these parts were focusing on saving power, right? Now let's look on saving time. So using the electronics for less time, which means putting electronics to sleep when we don't use it. So for example, micro sleep means you switch off power amplifier when no transmission is required. That can be done in microseconds in real time, that is. You can otherwise put the entire base station to sleep. If, for example, in the night, if there are 5 base stations in the area, maybe you switch 4 of them off and leave 1 on, because it's good enough. Right, and you can do power savings up to 73%. There are stages in between as well, so you don't. You can choose whether you're switching on just the power amplifier, or you're switching off some additional components like analog to digital converters, digital signal processing, or which would require you 1 millisecond to wake up or put it down. Or you can switch off more components on the front end, which would require you 10 milliseconds to wake it up. Or you can save, put more components in base station to sleep. BS stands here for base station. Right, so it's possible if you optimize this process. It was shown that it's possible to save up to 90% of energy at the expense of dropping throughput by only 3 to 19% during the low loads. Right. Okay, I'll skip more details on that. There are also more drastic approaches, like separating signaling and data transmission. So normally you have, say, 20 base stations in the area, right? And all of them have to transmit something. Normally, every base station has to transmit synchronization signals because your cell phone needs to know which base stations are nearby to connect, which base station it can connect to, right? But now, if you, which means you have to keep all of these base stations awake normally, if you want to have the good coverage. But now imagine if you separate signaling from data. In other words, there is one base station for a large area which provides signaling, synchronization signaling. And other base stations are just for the data, which means you can keep only 1 or 2 base stations, data base station up, and the rest of them can sleep. And it was shown that improvement was up to 4 times for this type of approach. One more note I wanted to make. So we spoke about wireless technologies. I wanted to make a mention, in the beginning of the talk, I mentioned the fiber is the best possible option because it will stay there for 100 years. It's fiber, it's doesn't, there are no interference which you can cause for fiber. Okay, maybe just with earthquakes, right? And energy efficiency, as you can see from these plots, is much better. So UMTS, it's your 3G. WiMAX, it was older from those ages. But the difference in power consumption is what? An order of magnitude. And why? Because again, in fiber or in wired connectivity, you only need to send your signal over through a specific fiber. Right. If you do things wirelessly, doesn't matter how narrow your beam is, it's not 0 degrees. It has certain bandwidth, and you need to spend energy to make it that narrow. So it will, I think, always be the same when your wireless connection will consume 10 times more power than wired connection. So these were the technical approaches, and are there other ways to reduce the power consumption, which are less technical? And the simplest is to use, as I mentioned earlier, use lower frequencies. So for example, to use lower frequency bands like 450 megahertz or 700 megahertz for rural areas, because your waves from your signals from base stations can go longer distances. Right, it also allowed to penetrate vegetation much better. This is the plot borrowed from ITU recommendations P833. And as you can see, frequency on the horizontal axis, specific attenuation in decibels per meter in vertical axis, and this is a curve. So the lower you're in frequency, the lower attenuation you experience. If I compare typical 5.8 gigahertz Wi-Fi versus 700 megahertz band, 700 megahertz allows you to penetrate 8 times more of trees and bush compared to 5.8 gigahertz. Also, if you look at the frequencies, this is propagation loss versus antenna heights. The higher you can put your antenna, the less propagation loss is experienced, the less power you need to push into that system. Right, but unfortunately, this approach is going to cost some money because building up a taller base station means it's going to be more expensive. Okay, let me skip on this. So another aspect which I wanted to highlight, I'm finishing the talk, is so we spoke about costs to build network, to run it. We spoke of how to reduce a particular component of that cost, which is energy consumption. Right. Now, if you think about it the other way around, is there a way to keep the business sustainable, to make mobile your network operate for you if you're providing commercial services without having to invest into upgrades, into even improving energy efficiency? Yes, there are ways to do that. To either postpone investing into upgrades or to get more money from upgrades. And that comes from the fact that despite the fact that I think about 5 billion people are covered with mobile networks, right? And around 3 billion people live within networks coverage, but do not use mobile internet. And only mere 750 million people live without any coverage. So the real problem is this 3 billion, not 750 million. And in my mind, the explanation is in the need to use the services. And here is an example. It is example borrowed from World Economic Forum. Measurements which were done on Facebook, right, on usage of Facebook in Tanzania. So Facebook in Tanzania had no user base, and very small user base until Facebook was introduced in Swahili. Swahili is the language predominant in Tanzania. 98% of population speaks Swahili. So suddenly, within just a few months, we got 500,000 users, and it continued to grow. That gives you an idea that how critical the language and literacy are in order to for people to adopt the technology, because the people need to see the technology is useful for them. If somebody speaks Hindi and sees and doesn't speak English and sees a web page in English, how useful is that page going to be for this person? Right, you can see immediately there is a barrier which needs to be tackled. If I dive it even deeper, right, here is statistics for India, for Africa, how many people never heard of internet or recognize the word of internet or know what internet is. Right, if I look at Africa, right, you have numbers from 43 to 75% of people who never heard of internet ever, and only 6 to 14% know what internet is. And in India, numbers are very similar. In other words, people need to know that it's useful for them, and they need to have the right language provided to them. And there is a good economic reason to invest into localizing technologies. As you can see, there is markets are huge. So in Africa, there is a good part of 1 billion people who are still not connected, and in South Asia is over 1 billion, and so on and so forth. So there is a good opportunity to grow the technology and make a real impact by localizing technology, by participating in research and development locally inside your country, in South Africa, in my case, in India, in your case. If there is interest to do collaboration, here are sample topics which we collaborated on and are collaborating on. In the past, that was about Wi-Fi mesh technology in television white spaces. Currently, we are looking into 4G, 5G, test beds, energy efficiency, network slicing. And the next steps, well, basically going in the direction, going towards the 6G, the next generation of mobile networks, which should be there within the next 4 or 5 years. With that, I would like to say thank you, namaste, and salam. And yeah, I look forward to the questions. Thank you.
So thank you, sir. Thank you so much for this wonderful presentation. And I have some questions here, sir. So, shall I ask a question?
Yes.
Yeah, okay.
Yes, please.
So this is my first question. How can the dynamic spectrum access techniques be optimized to improve the energy efficiency in wireless networks?
So how can dynamic spectrum access be used to improve network efficiency or power efficiency? Sorry, I didn't catch.
Okay.
Okay.
Then,
So
yeah, okay, sir.
okay, now let me maybe answer the question. All right. So dynamic spectrum access means that different frequency bands can be used within a geographic area, and you can dynamically allocate which band is used in which part at which period of time. So in my mind, it's possible to significantly improve the network efficiency by using dynamic spectrum access, because dynamic spectrum access means you're increasing spectrum efficiency, right? So you can provide higher bandwidth and serve more people by using dynamic spectrum access. So it's excellent tool for improving spectrum efficiency and improving the connectivity and basically coverage. Now, the amount of effect of dynamic spectrum access to improve the power efficiency would be limited. Why? Because yes, so you can, if you to use dynamic spectrum access means you need to have hardware which is expensive enough to be flexible, right? It should support different frequency bands. So, for example, lower frequency and higher frequencies. Say 2 frequency bands. If you want to save on energy consumption, there are 2 factors that would come into place. One factor is you would want to use typically lower frequencies, because then you don't need to transmit so much power. You can transmit less power. But that's as a foundation. But once you've done that, you need to monitor traffic and see how if the demand for the traffic is high, right? And if there are many collisions, then you would have to maybe try to also use, in some situations, other bands, not necessarily the lowest band, the bands which provide you wider bandwidth. Why? Because wider bandwidth means you have typically would have less errors, less congestion. So the main components would be to try to use the lower frequencies, but your system needs to be designed in a way to enable you to save power, right? It needs to be intelligent enough to drop the power to the level minimally necessary to provide connectivity. And if you want to just improve network efficiency, then you, well, it's a very straightforward approach. You optimally choose the bands and maximize the capacity and spectrum efficiency.
Yeah, okay. So thank you, sir. Yeah. So what are the latest advancements in energy harvesting technologies for wireless networks, and how do they impact overall network efficiency?
Okay, so when it comes to energy harvesting, there are two primary methods where how it is used. Right, in one method, you design a device to harvest energy from an arbitrary network. For example, from a typical TV broadcasting, or from FM broadcasting, or from mobile networks. In the second case, you design your energy harvesting device to be fed remotely with a directional antenna. So the main fight there is to improve efficiency of gathering the energy, and to right, there is also another aspect of how do you use the energy optimally. So once so you need to spend some time to accumulate the energy to harvest it. Say for 10 minutes you harvest energy, and then for a few milliseconds you can transmit a few bytes of information using the harvested energy, right? And now you need to select when you send this packet, because you don't want this packet to collide with packet from another node. So scheduling of when you send it is a research problem still. Then which frequency or which channel at which you do this transmission is also open research problem still. I think that's roughly where we are with energy harvesting. It's currently, because it offers so little amount of energy and can only do transmissions every 10 minutes or so at the best case scenario. Applications are somewhat limited. And if you want to increase the distance from 4 meters to, say, 20 meters, right? 4 meters to 20 meters, you increase it by 5 times, which means you need 25 times more power to cover the same distance. Which means instead of collecting energy for 10 minutes, you need to collect it for 240 minutes, which is 4 hours now. Right, so you increase distance, you need to collect energy for more time. So that's roughly where the state of the art is. Thank you.
Yeah, okay. So thank you, sir. Thank you so much. Then how can energy harvesting from ambient sources, like an example of solar or RF signals, be integrated into existing wireless networks infrastructures?
It's a rather complex question, and there is a lot of research ongoing there. And as I mentioned just now, most of this research is focusing on scheduling. Because as I mentioned, you can only transmit a few bytes of information, and you can only do transmission every few hours at best. Sometimes, if you want to cover longer distance, you probably need to collect energy for a week or for a month before you can transmit those few bytes. So you really want those bytes to count and not to be disrupted by other transmissions. So you need to schedule them in such a way as to ensure that when you transmit those few bytes, the channel is available, the channel is open for those transmissions. So I think that's the biggest challenge there. If you want to transmit those few bytes and those few bytes being received by some system, right? One is problem is scheduling. The second big problem is compatibility and complexity. The modern systems, if you look at 5G, right, as an example, your 5G standard is defined by 3GPP, the standardization body. And I think there are over 10,000 pages of technical documents defining the standards. As you can imagine, to implement those pages requires a lot of software code or hardware. And the more software code or hardware you have, the more energy you would need to run it through a processor, right? So compatibility with 5G would be extremely hard to implement using ambient energy harvesting, because you are, say you are harvesting for a month and you have only a few millijoules of energy which you harvested. So you need an extremely energy efficient processor in order to implement any complex code. So you have the only way the system can work is with simple enough implementations, where your code to implement the protocol, wireless protocol to support the system, has to be simple enough, not to be too extensive, to require a lot of processing power to compute all of the possible branches, combinations, and codes.
Sure. Okay. So, okay, sir. Thank you, sir. This is my last question. What are the most promising architectural changes in cellular networks aimed at reducing the energy consumption?
I think the most promising change has been, as I showed in the data earlier, in introduction of beamforming and massive MIMO. Why? Because the change allowed to make the beam narrow and to only send and exchange information with the users which require it. So you don't spread energy all around the base station unnecessarily. Many other changes. Okay, there are potential changes as which I mentioned. For example, okay, if support of lower frequency bands in 5G was a positive move, because at 450 megahertz you need less energy than in 2.1 gigahertz. Right. On the other hand, making 5G architecture more flexible. Remember, 5G compared to 4G became more function-based. Making it more flexible has effect, unfortunately, negative effect on energy consumption of the RAN implementation. But overall, you see, 5G managed to achieve better energy consumption per bit of information. So there, I think good work was done. But I think the question was about architecture, right? So the architecture, I think, supporting MIMO was the biggest way forward. And in the future, I believe working with decentralizing the architecture of mobile networks is a good way forward, good open research area to find optimal solutions to minimize energy consumption even more. Thank you.
Yeah, okay. So thank you, sir. Thank you so much. Thank you for the wonderful answers. So the answers are very useful. I hope the access and the participants can understand about that. So finally, so ladies and gentlemen, it's my distinct pleasure and honor to extend a heartfelt vote of thanks to our esteemed guest speaker, Dr. Albert, for his invaluable contribution to today's session on energy efficiency in wireless networks. Dr. Alberts, your expertise and insights have not only enlightened us, but also inspired us to think more deeply and about the future of wireless communications and the pivotal role of energy efficiency in shaping this future. So, Dr. Albert's extensive experience and groundbreaking work in the field, including his notable research in TV white spaces and the development of energy efficient 5G and 6G technologies, have provided us with a comprehensive understanding of the challenges and opportunities that lie ahead. So, your ability to translate the complex concepts into understandable and actionable insights has been truly remarkable and immensely beneficial to all of us here. So, we are profoundly grateful for your time and effort in preparing and delivering such a rich and engaging presentation, and your dedication to advancing the field of wireless communications and evidenced by your numerous publications, passions, and contributions to regulatory frameworks in multiple countries, and stand as a testament to your commitment to innovation and excellence. So your work is not only advances technology but also impacts countless lives by improving the access to reliable and sustainable communication networks. So, on behalf of everyone present, I would like extend our deepest gratitude to Institution Innovation Council Wales and thank you for the wonderful collaboration with your organization. So, thanks for the support and special thanks to Mr. Anandan and Mr. Satyanathan sir from Wales and Dr. Albert for sharing your knowledge and passion with us. We look forward to applying the valuable lessons learned today and continue to follow your pioneering work in this critical area. So thank you once again for your inspiring and thought-provoking presentation. And we wish you continue the success in all your future endeavors. So thank you, sir. Thank you so much.
Thank you, ma'am. Thank you, Dr. Robert, sir. Thank you very much for the session, sir. Thank you, ma'am. It's a nice session. The feedback about the session was very good, and I hope the participants enjoyed very much. Thank you. Thank you all.
Thank you, sir. Thank you so much. Yeah, thank you, sir.
Bye-bye.
Thank you, sir. Yeah, sure.
Okay, ma'am. Bye, ma'am. Thank you. Thank you, ma'am.